Hey math kids, today we're going to talk about roots of complex numbers, and so the all the roots are the solution to this. So if we call C the roots, they're the solution to this problem. And N will tell you the number of roots that you have, and there are exactly N roots. Okay, if C is a real number, then complex roots will be in conjugate pairs. If C is not real, then they won't. The modulus, so Z to the N, will have a modulus of C to the 1 over N, or the roots of this will have this modulus. And if we do an Argand diagram, so that's just like the real imaginary axis, we'll create a circle that has a radius that is this long, and on this circle the roots will be evenly spaced. So if there are 4 roots, they will make, and we connect those roots with line segments, they will make a regular polygon. Okay? So what they want us to do, they want us to find the 4 fourth roots of 1 by factoring and by the nth roots method. Okay, so on both of these we're going to start with z to the 4th equals 1. This one we're going to do it by factoring, so we're going to subtract 1. We do difference of squares, so z squared plus 1, z squared minus 1, and we could factor this one more time because this is technically a difference of squares, but we don't need to. So we subtract 1, z squared equals negative 1. We add 1 on this one. Z squared equals positive 1. Square root. Z is equal to plus or minus the square root of negative 1. And if we square root this one, z is equal to plus or minus the square root of 1. Then if we simplify both of those, this is plus or minus I. And this would just be plus or minus 1. Okay. So we have positive I, positive 1, negative 1. Those are the 4 roots. Okay. Coming over here, we're going to write this as in polar form. So 1, like on an Argand diagram, where this is real, imaginary. Purely real has a rotation of 0 or 2 pi or 4 pi or whatever. So we can write this as z to the 4th equals cis of 0 plus k 2 pi, where k is a integer. Okay, and then if we just simplify that, that's just going to be k 2 pi. Okay, we can raise both sides to the 1/4. Those cancel. Z is equal to cis k 2 pi raised to the 1/4. Negative 1, yeah, sorry, just raised to the 4th. Okay, now if we use de Moivre's theorem, we end up getting z is equal to this times by 1/4, which if we simplify that, k 2 pi over 4, okay, and then simplify that even further, the 2 and the 4, you get k pi halves, Now, because k gets to be, we're going to start at 0 and just kind of rotate around 4 times. We're going to get z is equal to cis 0, so if we plug in a 0, and then if we plug in a 1, we're going to get cis pi halves. If we plug in a 2, the 2's will cancel and we get cis pi. And then if we plug in a 3, we're going to get cis 3 pi halves. Okay. Now we just want to evaluate all of those. So remember, so cis 0 is going to be equal to cosine 0 plus I sine 0, which cosine of 0 is 1, sine of 0 is 0, so overall that's just a 1. Okay, now if we do cis pi halves, that's going to be cosine pi halves plus I sine pi halves. Pi halves is right here, which is 0, 1. So cosine goes to 0, sine goes to 1, so that's going to leave us with an I. Okay, now if we do cis pi, that's cosine pi plus I sine pi, and pi is right here, which is going to be -1, 0. So cosine goes to -1, this goes to 0, and so overall it's just -1. And the last one is cis 3 pi halves, which is going to be cosine 3 pi halves plus I sine 3 pi halves, which is down here, which is 0, -1. So this goes to 0, this is -1. -1 times I is -I. And so we get 1, -1, I, -I, which is the same thing that we got through factorization.